Hello and welcome. First off, I'd like to say thank you to my friends Paul and Claire Sheridan. If you look behind me on my shelf, my Mr. Potato Head now has eyes, so I'm really pleased with that. That's my Potato Head of Resilience. Maybe a YouTube video in the future will explain a little bit more. What am I going to go through today? So, at the last Repair Cafe session I ran, there was one of my friends from Scouts brought in a camping fridge. So this is a two-way camping fridge. It works off 12 volts and 240 volts. It's working fine on the 12 volts. So the socket that you have in your car, and for the older ones of us out there, referred to as the cigarette lighter socket, but very much frowned upon nowadays. So just the 12 volt socket. The 240 volt is plugging it into the mains, but that wasn't functioning at all. So I have a confession to make as well. So we're running out of time in Repair Cafe, so I rushed a little bit on this, much to the horror of one of my fellow repairers, Liam, watching me do something immensely stupid, which I'll share with you shortly. But hopefully you can sort of realise from my mistakes, so you won't make the same mistakes too. So this is semi-taken apart. It was a bit of a faff to get into. With many of these things, there's a lot of hidden screws, and on this particular unit, the screws, I think there were two that were visible, these two here, but there's an insulating rubber piece that goes all the way around, and that was covering in the channel, so we couldn't see the screws at first. Took this out, we found all the screws, took that apart, and what that showed us was the inner workings of the camping fridge. What you tend to find with camping fridges, they either work on two principles, either the Peltier module or Peltier effect, which is what this one works on because it's purely electric. So this unit here has a big metal plate underneath these fins. That metal plate is made of two semiconductor technologies, which when you apply voltage, one side becomes hot, one side becomes cold. So it has a fan in here which blows the heat through these fins. The other side of the Peltier panel becomes increasingly cold, which is what cools the fridge down. The other technology is absorption, I think it's called, where it tends to be for three-way camping fridges, which has 240 volts, 12 volts, and also gas. And the way that they work is a bit more like a traditional fridge or freezer, without a compressor though. So there's a heater at the back, either powered by the gas or powered by electricity, which heats up a mixture of ammonia and water. And as that cycles through a number of pipes, it sort of evaporates, goes through the pipes on the inside, condenses, and then takes away the heat on the inside as well. So both very useful if you're into camping. Obviously, this is electricity only, but the three-way fridges work off gas as well. So we checked out the obvious things, such as fuses. I checked the cabling for the 240 going all the way in. There wasn't any breaks in the cable. So what we found was on the power module inside, we found a blown fuse. So I will zoom in for you if I just switch cameras across, and then we can have a little look at what we could see. So if we can see here, on the board, there is a little glass fuse. Normally doesn't look like this. It's normally got a piece of glass in the middle, two metal endpoints, and we found that the glass had shattered and effectively the fuse had blown. We looked all around the fuse board. We couldn't see any obvious signs of damage. There was nothing burnt. None of the capacitors looked like they had bulged, which is a common sign of a faulty capacitor. We looked on the other side. Nothing obvious, although it does look like there's been some liquid damage around the circuit at some point. So maybe that is what's caused the trouble in the past. So my big mistake. We didn't have any of these fuses with tails. So I decided to bridge a fuse by putting the two metal pieces together and turn it on, see what happens. As soon as I did, a couple of the transistors at the back blew. There was a bit of a spark. Oddly though, after we turned it off, there was no burn marks, nothing like that, nothing obvious to show that there was a problem. However, not the best thing to do, not the wisest thing to do at all. So definitely don't do that. If you are going to have the theory of maybe you just need to replace the fuse, then just replace it with the correct size fuse. Because of all that would have happened if I'd done that is the next fuse would have blown and it would have protected the transistors and we'd have been okay. But hey ho, I learnt the hard way. So how do I know that the transistors are blown? So here's one of the blown transistors. See if I can bring my multimeter in shot as well. Now, when I use this in my first video, I didn't get any noise coming through the multimeter in continuity mode. But ultimately, what continuity mode does is it checks for resistance, and if the resistance is below about 50, I think, then it will make a beeping sound. So you may hear the beeping, you may not. If I put one probe on ground and just test a couple of the legs, we've got two of the legs that are going straight to ground. And the other way that we can check that as well is just put that across two legs. And you'll see on the multimeter it's reading 0.9, 0.8, 0.7. Oh, it keeps going down. So basically a short across the transistor. Now, just to prove, I have a new transistor here, ready to go into the new unit. So if I just check that as well, nothing. So that means that we don't have a short there. Now, if I check these two, that's fine as well. That one, that's fine. And then if you just check that, obviously that's going to be a short because they're connected on a transistor anyway. So I've blown the transistors, but what caused the original fault? Now that's the really important part, because if I put the new transistors in, replace the fuse, it's most likely going to just pop again and will be no further forwards. So what I did next was I spent some time having a bit of a probe around, see if I could find any other faulty components. And if you see here, I've already removed them, but two of the diodes I found had shorted, which was quite a lucky spot. And just show you what happens. So these are the original diodes. Just get them in shot for you and get the multimeter again so you can see. Again, if I check across the diode, which can be a bit tricky to do, you can see got dead short there as well. And if I get one of the replacement diodes, bring that across, try it again. Little things jumping around. No short. So we are all good. So the plan of attack is replace the transistors, replace the diodes, then give it a little test. Well, replace the fuse as well and not bridge it. I've got some new fuses, they're in the box. So replace that as well. So let's crack on. Right, what's the best way to do this so you can see what's happening? So these oddly, just to make our lives a little bit harder, the transistors have been put in like a triangular type pattern here with the three legs. You can see on the broken transistors, they have bent legs to suit. So you have to be careful with this. If you are bending transistors to fit into the through holes, the legs can break off. So just be quite gentle. So let's just move that out of the way. You can see what I'm doing. And maybe if I just bend this one forwards just ever so slightly, and then move the pliers down a little bit. That's probably way too much. So let's just try to be a bit more gentle. Bring that leg forwards, bring that one back. hopefully that will do. Do that on the second one. So again, bring it forwards and move the pliers down and bend it back. The reason why you sort of move forwards and bend back is just so you get that nice little kink in there, and everything will end up going straight through the holes in theory and be a bit neater, a bit tidier. So let's get these put in. Probably easier with a pair of tweezers. Again, massive selection of tweezers in my toolbox. Lots of different tweezers for lots of different applications. I tend to use my ceramic tweezers more than anything else, probably just because they're at the top, which is probably a self-fulfilling prophecy, isn't it? That the fact that the ones that are easiest to get to always get used. So let's get them in there. But I do like the ceramic tweezers because they are very good at helping you solder. The reason why is the ceramic tips don't transfer heat. So whenever you are soldering things, it is so much easier if all the heat goes into the point that you're actually soldering rather than being absorbed by your tweezers or anything else that you're holding your pieces with. So let's just pop those in as well. Gosh, they actually went in relatively easily. Now there's a couple of screws. These power transistors can get very hot, so they're often coupled onto metal pieces like this called a heatsink, and it allows them to operate quicker because it takes the heat away from the transistor. So it means the transistor can actually perform better because if they get very, very hot, and if it doesn't have the heat taken away, they can tend to blow, not catch on fire, so to speak, but definitely they would blow and become short. A little bit fiddly getting this one in. Gosh, I think I'm using the wrong screwdriver. So let's try a slightly larger screwdriver, see if that gives me a bit more security with the screw. There we go, a little bit happier. Still not the easiest to get in there. I think I am pressing down on the mat, which presses on the legs, which is causing the whole thing to jump up. Right, okay, right, let's get this screw out of there and go for plan B. If I turn it around and use gravity to help me instead of against me. So let's turn it around that way. Oh, stop beeping at me. Yeah, I noticed on my first video, the noise cancelling on my microphone is so good that despite the fact the multimeter is right next to me, it wasn't picking up the beeps. So I don't know if it's going to pick it up again. I'm not particularly keen on doing lots of test videos to see if things work, etc., etc. I know that some people might want a more slick video, but I'd rather just record as I'm going along and share my learning journey of not only fixing things, but also my learning journey of posting videos on online at the same time. Encourage other people to do. I really, really, really want people to share their knowledge. I've joined lots of Facebook groups, lots of sort of Reddit threads and things like that. I really do enjoy when I get advice and guidance from other people on how to fix things. Obviously, there are some people out there that are a little bit godlike, if you know what I mean. They like to impart their wisdom and never want to hear different points of view, but the majority of people in the repair community are open to suggestions and thoughts. And you know, there may be different paths to get to the same location, get to the same destination. So just because of you've taken a different route to get somewhere and you've still ended up at the same destination, doesn't mean that you're wrong. So there is more than one way to skin a cat, which I've never really understood where that saying comes from. I'm not sure there's many times I've thought about skinning cats. So yeah, maybe I'll Google that later and just have a look to see where that saying comes from. Right, so that's two transistors in. We'll obviously have to solder them up on the other side. But before I do that, I need to get the diodes in as well. Really important with diodes is that they go in the right way round. So effectively, you can think of a diode as a one-way valve. So if you put it in the wrong way, obviously that's not good. So let's get the legs bent over and get the other one bent over. Yeah, a lot of people get a bit scared of doing sort of electrics and things like that, but take your time. Lots of guidance on the internet. Always be safe. These diodes, although they are slightly smaller, they are the same spec as the ones that are in there. You will find that as more modern components come out, or different manufacturers will make them in slightly different ways, you will find that components are slightly different looking. So don't be worried about that. Just make sure that you've got the same product, the same model number on there. And sometimes, so these transistors were quite difficult to find. Had to order them off AliExpress with many other things that get off AliExpress, but you know, they weren't listed on eBay, weren't listed on Amazon, so obviously they are relatively rare. So you can't Google alternatives, and you can get lists of alternative transistors and things like that. I tend to want to try to use the original type if I can, but if I can't, I will go with the advice that I can find online. Right, okay, so let's get these soldered up, and also when we do this, we need to take out the fuse and maybe give it a bit of a clean to clean the board as well, get rid of some of this corrosion. What you can find with liquid damage is it can leave behind trace minerals. Those trace minerals can conduct electricity, and it's that conducting of electricity that can cause shorts to happen. And that's why liquids and electrics are generally a bad blend. You can get away with some liquids, such as IPA, which is isopropyl alcohol. Very, very, very common for it to be used in the repair industry. And the reason why is it's a solvent, it's really good at cleaning, and it doesn't conduct electricity. So as long as it's sort of 99% pure, then you can use that to clean electronics. It evaporates really quickly anyway, but also you don't need to worry about it being left on electronics, because the fact it doesn't conduct electricity, so it's absolutely fine. So next I'll put on some flux, and what flux does, it just helps the solder flow. I can't remember the exact way that it works, but it's something about removing the sort of oxidized layer off the components as you're soldering, and just makes the flux stick to those bits better. I quite like this flux in a syringe. It's from Chipquik. I've tried a number of their different fluxes. This seems to be the best one. Always looking for better, but it's quite disappointing when you get a flux that you don't like, because of it's not cheap, and yeah, you have to sort of solder on using a crap flux. So yeah, you don't want to spend money on things that you don't want to use too much. So coming in with the soldering iron, let's do these diodes first. My soldering iron tip has seen better days. I have got a new one, but I'm going to see if I can get the most out of this, as much as I possibly can. Let's turn up my extraction, because it's no doubt going to be a little bit smoky. Hopefully that's not too noisy for anyone. And let's get these soldered up. if you want to learn more about soldering and learn different soldering techniques and things like that, there's a really, really good YouTuber called Mr. Solder Fix. He has amazing skills, but also not only is he good, but he also shares his knowledge really, really well, shares the tips on how to do things. So whenever someone asks me, how do I solder? I'll always say go over to his channel because he's a brilliant teacher, a lovely, calm manner, quite mesmerizing sometimes watching his videos, but really, really good, good tips and tricks on how to solder. So that's Mr. Solder Flips. Right. Let's hope he doesn't see this video because he'd be shocked at how bad some of this is going. I'll come in and tidy this up in a second. Right, very conscious that if I put my hand in front of the camera, it focuses on my hand and not the soldering. So it's that gone on open. Let's see if I can reflow this one, because this is the one that I'm saying is not brilliant. Sometimes it's just a case of just finding the right place to get contact with your soldering iron. Try and use clean iron as well. It will go black very, very quickly. If you see like nice shiny tip like that, ignore the pitted hole that's in the end of my tip. If it's shiny, it's generally good and it will make good contact with the solder. But if it's oxidized, which it will do after a few joints, it doesn't transfer the heat anywhere near as well. So that looks like it's all soldered up okay. Now I've noticed one of the traces. So these copper lines that are underneath the solder mask, so the green sort of, lacquer that's on here is called solder mask, and then underneath it are all these traces or tracks, and they are just what connects the different points together. I've noticed this one looks like it's seen better days. Zoom in a little bit. Hands out the way, let it focus. Not quite sure what's happened there. So it looks deliberate, as in it's manufactured like that, but also it's not very typical. So I am just going to measure between those 2 points with a multimeter and just have a look to see what's going on there. If we've got continuity, then happy days. If we haven't, then we might need to do a little bit of trace repair. It looks like it's continuous. Yeah, so that's fine. That's fine. Okay, so what I'll do now is I'll just get my clippers and trim off the legs of those diodes. Then we can take the fuse out, replace the fuse. Probably should take the fuse out first. Hey ho. Well, I'll clip these off. It can be useful to keep these legs, not for today's repair, but the amount of times that you might want to do something. These little bits of wire are sort of perfect size. They're brilliant for repairing traces on these sort of bigger boards. So if that trace had broken, I've used it to go across like that. So they are quite useful to have just a small supply of them, although 2 of them seem to have gone missing. Right, let's turn the extraction off for a second. All right, let's see where that fuse is. The fuse is here, looking a little bit sorry for itself. So those 2 points, just need to desolder them, pull the fuse out, and then put a new fuse in place. So to do this, I'll use a bit of solder wick, show you how I use it. And this is where having the ceramic tweezers is quite good. and they don't conduct heat as much as metal tweezers, and desoldering things can be a bit of an art in itself. I've struggled with it many times in the past. Very much comes down to what the solder was like that was used. Games consoles, the controllers on those, they are notoriously difficult to get the solder off. And if you've ever tried to replace a joystick on a games console, you'll know that there's about 1 million solder points to take off. So it's a little bit fiddly. Right, let's just get a little bit of flux on there. A little bit of flux on there as well. Then if I get my tweezers, pick up the solder braid, then turn on the extraction because there is quite a lot of flux to be sucked up. Give my soldering iron a good clean on the copper bristles. Then just come in here, apply some heat. Then hopefully you'll start seeing the solder go into the solder braid. There we go. You'll see the solder braid go silver, and the solder has started to come off the legs of the fuse. Do the other one. And we might still find that the fuse doesn't go straight through, but it just takes a little bit of persuasion sometimes. So let's see if we can just pull it out as it is. Turn it around so you guys can see. Actually, it's quite loose, so we might get lucky and have done this first time. Let's see if I pull that out. There we go. Happy days. So you can see my lovely job of bridging a fuse together. I will definitely never do that again before everyone starts pointing out I should never have done it in the first place. Okay, right, let's get the fuses out the box. 1 second. Here we go, came in a pack of 10. And that's what they should look like. Let's get one out. Quite often the fuses are marked on the fuse themselves. Will it focus? Will it focus? No. That's a bit annoying. I'll stick my finger behind it. So you can see the writing on it, just about 2.5 amps. So generally they're written on the fuse, or you might also find that it's written on the board itself. So you can see here, I know it's upside down, but 2.5 amps, 250 volts. So if you are going to replace a fuse, make sure you've got the right rating for the current, which is measured in amps, but also make sure you've got the right voltage measurement as well. So when I bought these off Amazon, they are rated at both those values. So this is a perfect replacement. Let's pop that in there. I will also mention that power boards like this tend to be my nemesis, so I never have much luck with them. I'm hoping that I get this one sorted, but even if I don't, I'm going to post a video. Maybe someone can help give me some advice. So, right, what am I doing next? A bit more flux. The flux burns off really quickly, so you do need to put fresh flux every time you do something. You can get away with soldering without flux, but why make your life harder if you don't need to? So just cleaning my tip of my solder. So just soldering iron. So just so you know what I'm doing. So I've got copper pad there, and some copper brushes. Give it a good clean. Happy days, nice and clean. Then come across, get this soldered up. Then I can dig out the AC power cable, connect it to this board, and see if we are getting, I assume this should be 12 volts coming out the other side. But even if it's, I don't know, 24 volts or something like that, at least we know it's working rather than nothing at all. Okay, right. Get these legs trimmed off. There we go. Not quite sure what all of these bits on this board do. So maybe I should switch to a different camera so you can see what's going on a bit better. Let's try this one so you see the whole desk. Move my close-up camera away for the moment. So that's the board. Let's turn off the fume extraction. So here we have the board. So we definitely, this is just a normal sort of power board. You'll see on this side, it comes in two halves. Where's my pointer? I've lost my pointer. There we go. So it has what we call a hot side and then a not hot side, a cold side. But ultimately, it's the high voltage side. So the mains voltage comes in on this side. It goes through some rectifying diodes. And what that does, it translates it from AC across to DC, but you're still operating with high voltage DC current, and goes through some capacitors to smooth it. So you've not got lots of well, lumps and bumps, noise, whatever you want to call it, but it smooths it so you get a nicer sort of flow of DC electricity. Comes across to these transformers, which will transform it down to a lower voltage. Again, goes through some other components here to clean the electricity before it goes out. And then also there's some components on here to make sure there's nothing that flows back into the mains, which causes sort of the mains to be, I guess, effectively poisoned by lumpy, bumpy voltage from your power supply. So, right, let's see if I can get the mains cable out of the fridge. So let's change across to here so you can see what I'm doing. Maybe I should have done this before doing the video. But you know, right, okay, it's clipped in there. Let's just get that undone. We are going to be working with mains voltage, so we have to be really, really careful with this. If you're not confident with it, don't do it. Go to your local repair cafe. They can help you. They can talk you through this sort of thing, or a repair shop. Obviously, if you go to a shop, it's going to cost you some cash. I'm not sure how much this camping fridge costs, but going to a repair shop where they charge you is probably prohibitive compared to the cost of the appliance itself. Right, that's the mains cable through. Tangled up down there. Okay, right. I've got a couple of sockets on the front of my desk, which just makes it easier for me to do some of this work. Then if we switch back, and all I've got to do is connect the end of the mains lead to this point. It's not, the mains isn't turned on at the moment. Then we've got the output terminals there. So to make this a little bit safer, I have some crocodile clips for my multimeter. Oh, not crocodile clips, they're clips. Let's see what I can find. Where are they? Where are they? Buried at the bottom with everything else. Right, so I've got some of these clips which allow me to clip onto the end of the wires. Let's get that clipped on there. And what this means, I can power on the board without having to touch anything. And it makes everything that much safer. So switch that to DC voltage. Hopefully you can see that. Right, okay, should we turn it on and see what happens? Nothing. Brilliant. Well, that's not good, is it? Okay. Right, let's see. Nothing sparked, which is good. But maybe we need to test to see if there's anything going across this power supply. So, right, let's turn the mains off. Actually, I don't even know if that is definitely the mains coming out. What's this say? NTC. So that's probably a temperature probe of some sort for controlling things to go on and off. I definitely think this is what goes off to the Peltier module. Let's move that out of the way. What might have happened is through my ridiculous attempt of just doing a quick check, I may have fried the IC on the board. If I have, I'll have to start looking at data sheets and go out the oscilloscope and all sorts. So, right, let's safety first. These capacitors are 200 volts and they will no doubt be full of electricity. So let's just turn that over carefully. Let's just check to see what's in these caps. You see my multimeter? Yep. All right, okay, they haven't got any voltage. That one hasn't, at least. And then let's check this one. That's not got any voltage either. Okay, so maybe the voltage hasn't gotten through to them. What else do we have going on here? So let's just check. Let's take the mains power off and just check to see for continuity between different things. So I'm going to assume one of these goes to the fuse. Nope. Nope. Oh, hang on, I've got this on the wrong. There we go, hang on. Right, let's try it on the right setting. Yeah, that goes through to the fuse. That's continuous. That shouldn't go. So happy days, that goes through to there. Where does the fuse go after that? So it goes from this pin to that pin to there, across to there. Let's just see if these are continuous. Yep, that's working. That's continuous. That's continuous. Yep, yep. Then where does that go? Into this small little transformer, which then goes through those 4 diodes. Let's see what's going on there. I said that switch supply is my nemesis. That's okay. That's all okay. That's okay. That's okay. That's okay. 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 So if I turn that over, what is that doing? So that's going through to those diodes. Let's check the diodes again. So diodes, you need the multimeter in diode mode. You should get a reading one way. Check. And then turn the probes over. You should get nothing the other way. Good. Check that one. Nothing. Good. Turn over. Reading. Yep. Reading. Reading. And then check the other way. Yep. Nothing. Let's just double check the right way around. Yep. Right, so where do these diodes go after? So they come down here, across to a resistor, which comes across down to here. We must be getting to these capacitors soon. So I think the voltage will be getting all the way through to this resistor, which comes across to here, which also links up here. So did those capacitors charge when it was plugged in? Could we have some blown capacitors as well? Let's see. So really careful now. We will be putting mains voltage into the board. That's turned off currently. And then doing some probing whilst it's on the board. There's some rust on the contact to this capacitor on the solder point. Ah, interesting. It's even connected. There's nothing on that capacitor. And that one. Right, let's check the AC coming in. So it's these two lines here. Nothing. Right, okay, maybe we have another problem with the cable. So there to there, there to there. Right, we're getting nothing on the actual input. So let's check this cable. Did the fuse blow in the plug when I did my fuse special? Could it be as simple as that? Let's take this off. A couple of ways we can try is let's just check for continuity between the end here and the actual plug end. So right, continuity there, and on the live, nothing. Could mean that the fuse is blown inside the plug. Let's just, actually we can test it there and then, can't we? Beeping. Yeah, the fuse is blown as well. That's really good. So 3 amp fuse, nice to see. Always replace fuses with the correct fuse rating. The amount of times that you see someone that's just putting a 13 amp fuse into a 3 amp fuse plug, and then, well, ultimately you could end up with way too much power going into the device that you are powering. So I've just got to come across to my box of bits to dig out the fuses. I have a big trolley case of spares and tools and things like that that I take to repair cafe with me, and that's got my fuse box in there. Right, what have we got? Here we go. One of these days when I'm rich, I'll have drawers full of these things so I can just get to them straight away. But at the moment, they're all stored in a big box. Here we go. There's fuses. Right, what have we got here? Is that 3? There we go, we've got a 3. Wipe that into the plug. Put the cover on. Let's get that in down there. Let's go again. Right, let's get our safety leads. Is that turned off? Yes. Let's get this set up. We did check the fuse originally, so it's definitely blue when I did my stupid mistake. Oh, stop beeping. Thank you. Let's turn that to voltage DC. You guys can still see. Here we go. Let's see what happens. Nothing, but there's a clicking noise coming from something. So there's definitely power going in because of the fact that something is clicking away. I don't know if you can hear that on the mic, probably not with all the noise cancelling going on. So let's go back to our checks. Let's just turn that off for a second. Remember, no power that is going in means that those capacitors are probably charged up now. So very, very carefully turn this over. We're on voltage DC. It is turned off at the moment. But if I do this, I mean, you can see the voltage coming down relatively quickly, but you will find that some capacitors will hold on to their charge for quite a long time. I've had devices that have been plugged in days ago, and then you go to test the capacitors and see that it's still got hundreds of volts in there. So you've got to be really, really careful. So we do have voltage going through to capacitors, which is good. Right, where do we go next? Do we see what is going on? Right. Okay, so where do the capacitors go? That goes across to there, across. Capacitors then. Shall we see what's coming out of those transistors? Right, I said that power boards are my nemesis. So let's see if we are getting any voltage coming across to the transformer elements. That's still on DC. So I'm going to guess. Right, we've got no voltage across that one. Nothing there. 277 volts there. 277 volts there. So is that up mid transformer? So nothing's going through to the big transformer. So what comes across to the cold side from that one? Let's see. Anything? Nothing. Nothing. So we're getting 1.5 volts. 1.5 volts. So jumps if I don't connect to, well, so let's turn that off. Right, I'm going to pause there for a minute just so I can start looking into what to look at next to see the next part to investigate, and then I will be back. Okay, speak soon. Hello, I'm back. Spent last couple of days doing a bit of Googling and also a few tests. I didn't want to bore people too much by watching me tear my hair out and try to understand what I'm doing. I'll cover what I've done so far and then take you through the different bits of tests. I don't think in this part of the video I will finish off fixing the power supply, but we'll see where we get to and go from there. So if I do a quick close-up of the power supply, I think to explain what I was doing. So hang on, the camera seems to want to do its own thing. So if I do that there, okay, so how to explain a power supply in this case. Some people may just say, why don't you have a big, massive transformer? Well, because they are big and they are massive. They are heavy, they heat up quite a lot. They can do the job of converting mains power down to 12 volt DC, but they're very inefficient. So what has progressed over the years is miniaturization of power supplies, and the way that is done is by introducing effectively a head shaft, And in this case, the head shaft is this integrated circuit just here. It's a little chip, and the chip is what controls a lot of what goes on this board. Now, you saw in the first part of the video that we got power to go into this board, but we were getting a clicking noise. That clicking noise is an indication that there's something wrong, and it's shutting itself down because it detects a fault. It does that many times a minute, and that shutdown and startup, also known as a hiccup, just sounds like a clicking noise. I'm not sure if you picked that up on the microphone earlier, but that's what it was doing. So we know that it's not starting up successfully for one reason or the other. What had been done so far is we replaced the fuse just here. We replaced the transistors as well, but there was still something not quite right. Why was the board clicking? So there's a few things that we could start theorizing and inspecting, but from what I've seen in the past, it always seems to come down to this chip here is not functioning properly for some reason. And the first thing that I'd always check is to have a look to see if this chip is actually getting the correct startup voltage. These chips require a particular voltage to start. It might be 5 volts, it might be 12, it might be 20. And the way that that is done is there is a smaller transformer, and the smaller transformer will provide a trickle voltage to this chip, just enough to get it going. And then once it's going, it then controls the main part of the circuit, which will send the clean power out to your device. So we know that this chip, or we suspect this chip, is not happy for some reason. So first protocol is to look at the chip number and then find a data sheet. Frustratingly, this chip is a proprietary chip to a particular manufacturer. So the manufacturer will create chips, put part numbers on there, but don't necessarily share the data sheets. What I've been able to find out is that this chip is quite a common chip, but mostly is known by a different number, which is, if I switch to the data sheet for it, the number is CM6800, which is quite a common current controller. The important bits from the datasheet will have pages and pages and pages of specs, but what we want to see is how much power does it take to start up this chip. So we'll see on here, it's got a voltage in, which is this VCC. The next page will show us that. So VCC is the power in, and ground is ground, obviously. So if I just scroll to the next page, we have, where is it? VCC, the positive supply, and that's what goes through to the chip. It says minimum 10, maximum 18, typical 15. So they're the sort of ranges that you'd expect to see on the chip getting to the chip. Now, there's another piece of information that is really useful on the data sheet, and that will be something called a startup current. So there's startup voltage, which is normally the minimum voltage that it takes to kick the chip into life. So if we scroll through the data sheet, lots and lots and lots of information in here. See if I can find somewhere that talks about a startup current. Here we go, near the bottom. Hopefully you can see my mouse wiggling around. Startup current 12 volts. So we would expect this chip to be served at least 12 volts when it starts. And then if we go back to the VCC, and then it should keep operating around about 10 volts up to a maximum of 18. Typically, these chips will have some form of protection in them. So if you're too low, they will shut themselves down. If they're too high, they'll shut themselves down. If it's massively too high, you can end up with a short circuit in your chip. So if we come back to the chip itself, we now know what this chip takes to start and what it takes to go. So what I did was I looked at the pins and I looked for the input voltage for this chip. So if you remember back on that page, VCC, if I go back to the pin out so I can remember which pin it was on. So pin number 13, let me just toggle for you so you can see on the browser, pin number 13. So you can see there's a semicircle, and starting from the left, it's 1 to 8, and on the right, it's 9 to 16. So you count down on the left and up on the right. So let's go back to the close-up. So what we want to do is the little semicircle divot in the chip is up here. You may not be able to see on the close-up. And then we can count down on the left. So that's 1 to 8, then count up on the right. Or because we know it's a 16 pin chip, so we can go 16, 15, 14, 13. So I put my positive probe and the multimeter on there, and the ground pin is pin number 10, and I'll just check the voltage. Now, when I did that, I found that the voltage was only 1.5 volts. So I know this chip, for some reason, is not getting the right voltage. Can be one of two things. There may be something around this area that's causing a short circuit and is eating up all that voltage, and it means that this chip just never gets up to the right voltage. Or it could mean that somewhere on the trickle voltage that's coming into the chip, there's a problem. So my first protocol was, well, let's go and measure the resistors and the diodes that are on the trickle line that go to the chip and just see if we have any problems. So I'll just show you a couple of measurements so you can see. So if I just switch the multimeter across to resistance, the ohms, and I'll be checking a couple of the resistors on the way in. Now what you'll see, if I go back to the closer, is I've done what's called lifting the legs. These resistors, I've desoldered one side just so I can get an accurate reading. If the resistor is plugged into the board on both sides, then there's a good chance that not only you'll be measuring the resistor, but also you'll be measuring a lot of the circuitry that goes around. I did do that to begin with, but I found that these resistors were measuring in the mega ohms, and that didn't seem quite right. We'd be looking at in the sort of roughly 100 to 200, maybe 300 kilo ohms. So if we, now that we've lifted the leg of this resistor, do a check, measures, let's get the probes on steadily, measures 177, so it's probably 175 kilo ohm resistor. So I did that with a number of the resistors that were going through. These big resistors are power resistors. Let me just go back to the desk and show you the measurement on the multimeter so you can actually see. There we go, 177.7 kilo ohms. Now the other things that I would normally check on the way through up to this chip is the small diodes. They're called Zener diodes in this case because they're small glass diodes with sort of orange and black markings on them. And the way to test them is switch this across to diode mode so your dial stays in the same place on this particular multimeter at least. And then you switch it to somewhere where it's got a symbol that shows like a small triangle and a line. So it shows that voltage is flowing in one direction because that's typically how diodes respond. So onto one of these diodes, let me zoom in so you can see what a diode looks like. It's these small components that are orange and black. You'll see them all the way across the board. You can see how many I've lifted to test, so I didn't really want to bore everyone with that. So if we go back to the desk view only, and I'm just going to put my probes on either end of one of the diodes, and we can see it measures 0.587 volts. And if I switch the probes around, we ought to see nothing flow because diodes only let electricity flow in one direction. And there we go, nothing is going through. So I worked my way through, checked all of the resistors, checked the Zener diodes, and I found nothing's wrong. Right, well, what else could be causing the voltage to drop? The next common thing that might happen is the capacitors. So there are a number of capacitors that sit around the IC. If one of those have shorted, or if one of them has a fault within the capacitor, it may mean that that's gobbling up all of the voltage and stopping enough voltage from getting to the chip. So the next thing that I did was desoldered the capacitors around the integrated circuit. And if I go back to the desk view, you'll see that they're all sat up here. So I've got the fun job of putting them all back in. Actually, if we go back to close-ups, you can actually see what one of these looks like. So got the capacitor there, find it right in the camera, let it focus. You can see it's got markings on the sides that tells you the capacitance and the voltage at which it's rated. So the voltage just means not to put any more than 25 volts through there. And it's got a capacitance of 47 microfarads. The five capacitors that I took off all have slightly different parameters on them. So they have different voltages and different capacitance. So one of the best ways to measure a capacitor is with a ESR meter. Lots of different ones out there. So put one probe on one end, one on the other, and then turn it on to test. And there we go, capacitance of 43.84 and an ESR reading of 0.51. So the capacitance is it's within about 10% tolerance, so that's not bad. So that's okay. It's a bit low compared to the fact it's meant to be a 47 microfarad capacitor. The ESR is a measure of the resistance within the capacitor itself. So what you're looking for here is a low value. So 0.5 ohm is relatively low. So I would say that's got a good ESR. Still can be tricky measuring capacitors. If it's a newish device like this, I would say that's quite good. If you're working on antique electronics, even if you get a good reading, if the capacitors are 20, 30 years old, I would replace them anyway. If you've got an appliance open that is that old, it's just worth replacing them because you've got the time to do it whilst the device is open. So the capacitors are good. One thing to tell you about capacitors is they're called electrolytic capacitors, and that's because effectively they are a roll, I should say, a roll of a substance with an insulator in there, but it also has a liquid in there, an electrolytic liquid that allows electricity to flow and also to be stored within the capacitor. Now that liquid can degrade over time, and effectively capacitors can go bad. So you look at them and you think, no, they don't contain liquid. So it's not runny, but they can be known to leak. They can be known to pop out at the top. You'll notice on these bigger capacitors, they've got grooves in the top. And effectively, that's to allow, when they go bad, that's to allow gases to escape or a liquid to escape. So if these short circuit, they can sometimes short circuit and these top bits pop off. You can open up a device and see that across the top of the capacitor, it might be bulged. I've never seen one bulged at the top, but I've certainly seen them bulged at the bottom where the gases and the liquids have expanded over time and they just need to be replaced. So, tested the capacitors. I have tested the resistors. Everything was okay. What is left to test? There was one more component that could have been a smoking gun, which was a big transistor that just sat down here. So I took that off. Again, it's always easier to take things off to test them whenever they're in the circuit. You're not only testing what's under test, like the component itself, but you may also be picking up readings from elsewhere on the device. So going to switch this across to diode mode. In the simplest form, transistors are sort of diodes that operate in different ways. So what I always do is just do a test between the middle leg and the outside legs. So we've got a reading of 0.115 volts in that direction, and because we suspect it may be acting like a diode, nothing there. Check there, nothing, and then switch the probes over, nothing again. The other check I would do is just to see if there's a short circuit. So I'll just check continuity to see if any of these are shorted, which I don't think they will be because of the fact that we have just done the diode test on them, and just to prove that the middle leg's connected to the back. There we go. Hopefully you can hear that. If not, you should be able to see a very low ohm reading on the multimeter. So we've done all these tests and nothing has been found to be faulty. So what next? Now this is where it can get a little bit more involved. So one other thing that could be gobbling up all the current is the chip itself. So if the chip is short-circuited, effectively it becomes I don't know, becomes a radiator, I guess. You know, the wires will short circuit and heat up. So one telltale sign is, does the chip get warm after it's been left on for a period of time? That can tell us if it is short circuited. Another thing that we can do to test is actually put some voltage into the chip and have a look to see the behavior of the other legs and see if there's a leg there that we can measure to see if we get anything out. Now, I think the simplest test that I did was ultimately, I connected the chip to my bench power supply, and I'll show you that in a moment. So we were, what was it, pin 13 for the positive. These probes are a little bit fiddly. So 16, 15, 14, 13. What I've found with these little probes is that they pop off. Right, that's on 13. Let me go into the close-up view so you can see what I'm doing a bit better. And let me just show you the ends of this. Can you see? It's not terribly good because it's focusing on my hands. There are these little probes that pop out and you can clamp them onto your chip. So where are we? And we want ground, pin 10. So we know it starts at 9, so it'd be the second from the bottom. Really fiddly to get this on. But what you want to make sure of is that when you're doing something like this, you don't touch two legs together, because of if you bridge across two legs, you could in effect, cause the short circuit and fry your own chip. And some of us might like our chips fried, but I would much prefer not to break these chips because they can be a bit of a pain to get hold of. Right, okay. Right, so we've got one on there, one on the other. We know it needs a startup voltage of 12 volts. So if I just show you on my bench power supply, just here. So I will set that to, let's see what we've got this on at the minute. So let's see. Have we got any pre-programmed ones? No. Right, okay, so I can set this to 12 volts. keep the amps really, really low, and then we can turn it on. In theory, if the chip is not shorted, we should see this amp reading be quite low, as in lower than it is now. If it's shorted, then we'll see this relatively high, all the way up to 50. So let's turn this on. And there we go. So it's drawing 9 volts, but it's also consuming 0.049 amps. And the reason why it's not consuming more amps is because of the fact that I've set this bench power supply to be low, which means that it will effectively not consume more than I will supply it. If I put that up to, I don't know, 13 amps, then we definitely see some fireworks happening on the board. So I very much suspect that chip is fried. If I leave it on for a while, I could probably feel my finger, the chip getting warm. It takes a little while for it to heat up to the point where you can actually feel it, especially at a low current like we've got there. So what I do have is, I'll just switch cameras. What I do have is a thermal camera. So if I just get that out, it attaches to my phone that I use for the close-ups. So you'll have to wait one moment whilst I switch across. Little FLIR camera, quite good. Got it off eBay, not a bad price. I actually bought a broken one in the hope that I could fix it. I did get one cheap that was broken, but it was beyond my skills and it was so tiny. I still got it in bits. Maybe one day I will learn enough to be able to fix it and get it working. So let's get this one going. So it connects to the bottom of your iPhone or whatever phone you want to use. This one's got a lightning connector on it because my iPhone's relatively old. And then once it's loaded up, oh, come on. Here we go. Is it going to power up? Here we go, here we go, here we go. So we get a nice thermal picture. So if I switch back to the desktop mode, and then hopefully you can see, I mean, straight away, you should be able to see there. Can I zoom this in? Oh, this is awkward. So if you see on the FLIR cam, we have a hotspot just here. It says it's 35 degrees. And what's that hotspot correspond to? You can see my hand there. You can see how warm that chip is getting. So that chip is slowly heating up. Chip is definitely fried. It's definitely short-circuited. So next thing we need to do is replace that chip, see what happens, and hopefully we will have a working power supply. So what I'll do that off camera, or at least I'll put the components back in off camera. I'll do the chip on camera. So let me just get all the resistors back on, the transistor back on. Then I'll take the IC off on camera and put the other one back on so you can see the techniques that I use to do that. And then fingers crossed, we'll be able to get this working. So there will be part 3 coming soon. Okay, I'm back and I've got all the pieces soldered onto the board. I've left the IC in place. It needs a bit of a clean afterwards, but I thought I'd do that after I do the IC. But I've got all the components that I lifted the legs back on. So now I need to work out how to take off the IC. There's a number of different ways to do it. You could use solder braid that I've shown previously to take away some of the solder, or there are some other techniques, but I've got a desoldering gun and I'm starting to feel a little bit impatient. So I'm going to use that to take off the IC. So if I just switch across to my desk view, just move my close-up cam out of the way. So this is a soldering gun. Effectively, it's a hot tip at the end, and it's a vacuum. So if I put my hand on there, it would suck my skin, but it would also burn me horribly. So I'm not going to do that. Just going to work through all of the legs of the IC and get all this desoldered. Oh, hang on, let me put on my extraction as well, so I don't have to suffer the fumes. Sometimes solder guns, they work really, really well. Sometimes you have to go over afterwards and just finish up so it's not picked up. Once I've done one side, I'll share a close-up image so you can see what the solder gun's done. Sounds like it might have a little... No, it's done that one okay. So I might need to put some flux on here to just get the solder to flow just nicely. So bring the close-up cam back in. Let me show you what's happened so far. So where are we? Where are we? So I'm not sure if you can see. Let it focus. If we just see here, it starts to take the solder off, but there's a couple of pins that it's not fully come off. So I'll just add some flux and try and desolder those and just finish the chip off. And the flux can just help it flow a little bit more nicely. I try not to use too much flux when I'm using this gun. I don't know if it makes much difference to the filter in the gun, but I don't want to be having to replace the filters all the time. Sometimes if the pins are bent and you can't get the nozzle, it can be a bit tricky. Very nice. It's always good to get the tip of the nozzle as flat against the board as possible, just so it can transfer the heat. Heat is both your friend and your enemy when you're soldering. So a lot of soldering is all about holding the damn thing still, making sure everything's clean and prepped, and just making sure that you're applying heat in the right place and controlling that heat as best you can. Right, again, there's some pins here that have not gone. What temperature have we got then? So it's on full whack. There we go, that's a bit nicer. Getting there. Most of the legs are done, but there's a couple that are not playing ball too much. And it is important to get the solder off as much as possible, because if you don't, you might break the connections on the board. I know the IC itself is to be thrown away, but you don't want to damage the board itself, because if you do, you have to get into start to repair boards, and that's a whole different ball. There we go, that looks good on that side. Maybe this one, just one more time. Give it a little bit of time to heat that solder and get it nice and liquid. Give it a suck through the gun. Right, let's see if we can lift that off the board now. Various tools for lifting things off the board. I've got these chip pullers, just like tweezers, but with sort of L-shaped ends at the end. Oh, I can already see there's going to be a problem because if there are components in the way, might have to think of a plan B. Right, one end's up. I'll pull the chip that way. Right, let's get a pair of pliers. There we go. Happy days. Always important to look at the orientation of the chip before you take it off. Now, most boards will have, so most boards will have indications on the board. So let me just show you. So on this board, you can see where the chips come off, and there's a nice little divot printed on the board, so you can see quite nicely which orientation the chip will need to go. So if I get the replacement chip, as you can see on here, it's got a little divot on the end, so we know that this chip goes that way round. Let's place it in the board, and we'll get it soldered up, and then hopefully the whole thing will work. Now, sometimes what you'll find is when the chips come, their legs are a little bit splayed out. So we need to be careful how we put that into the board, because the last thing you want to do is damage any of the pins. Just move the camera out of the way again. So don't just go gung-ho and press it in as hard as you can. You just got to make sure that the legs line up, and you can gently ease it in to the holes. Yeah, some of these legs are misaligned a little bit, so if I just try and change the orientation of the chip a little bit, I might need to take it out altogether to adjust the legs. It's so close. So close. Will it? So come on. Right, what have I got to prod these in with? Pair of tweezers. See if I can just. So some of the legs are lined up and some are just slightly off. So I'm trying to be making as small a change as possible. There we go. Chip has gone in. Turn it over. And you can watch me solder the legs on. Do that just under my extraction. Turn that on so you're not getting fumes everywhere. A little bit of flux on all of the legs. Get the solder ready. And the soldering going on. Nearly there. Looking good. Should give it a bit of a clean, but I'm quite eager to get this tested. So, right, let's switch the cameras again. Pop that over there. I did create a little test bulb. No idea where I've put the damn thing. Oh, my desk is a mess at the minute. I think what I'm learning is I desperately need somewhere to work and spread out a little bit more. So I've created this. It's a small 12-volt bulb. It's I think it's an indicator bulb, or it's a reverse light bulb or something from old-fashioned cars. So it's an incandescent bulb. You don't want an LED. You want something that will actually carry a load. So I've got that as my test load for the board. Switch across to the desk. Connect this across. I'm just going to find where I put the AC cable. Did that tidy it? Oh, yes, I did. It's in here. It's back in the fridge. Okay, so just going to plug it into my test socket at the front. Connect it to the board. Keep everything clear. Make sure that's clear of everything. Let's give it a turn on and see what happens. Nothing. Oh my days. Okay, right. Let's get the multimeter and see if anything is actually happening anywhere on this board. Volts DC. First things first, let's just test these connections. Nothing really. That's disappointing. So let's see what's happening on the IC. Remember that this is live. You need to be uber careful. So let's see what voltages are coming into the chip. So it was chip. There's the data sheet. Let me just find the data sheet to go back to. Just having a look on my laptop. Oh, there it is. It was hidden away in the back. So let's go back to the desktop browser. Data sheets, we want pin 10 and pin 13. So we want to probe on pin 10. So pin 10 is one up from the bottom on the right of the chip. 10, 11, 12, 13. The chip is not getting any voltage in. What has gone wrong this time? Well, if the chip's not receiving voltage, then it definitely won't work, will it? Let's just test to see, have we actually got AC coming into the device itself? It looks like we don't. It's a bit weird. I've got that turned on. Let's go down there. Let's just turn it over and check the AC pins on the other side. Okay, so bizarre. Let's turn it off. Have we popped the fuse on this again? Check for continuity. Yeah, this fuse is gone. No, it hasn't. No, it hasn't. It's absolutely fine. Fuse is good. Pop it back in. But for some reason, AC is not getting through to the board. And is that in? Okay. Turn that on. Switch back to AC. There is the AC on the board. It's these two here. Nothing still. How peculiar. Right, let's turn that off. So the power is still coming through to the socket. Let's turn that off altogether. Let's have a look at the something gone odd with these pins. Right, let's check continuity because I've noticed there's quite severe clamping on this cable from the strain relief. So let's just see if we've got continuity between the two ends. Oh, this is definitely the gift that keeps giving, isn't it? Oh well, some repairs are like this, aren't they? Now let's turn off the fume extraction because that's well noisy. So that's fine. Let's check the other one. And that's fine. Right. Maybe it wasn't connected to the board properly. Right, belt and braces. Let's just check. We are getting AC through here. Yep, it's coming through to the end of the cable. Let's just turn it off before I electrocute myself. Had I just not connected it on the end here properly? Let's have a look. All right, okay, maybe these pins were a little bit funny and I hadn't got it securely attached. Turn the board over to check. Turn it on, still nothing on the bulb. Let's check these pins. Still nothing. What? Right, so those pins are definitely on the bottom of well, this is a mystery. Definitely turned on there. Right, let's try again. Connected there, let's see. So it flashed up for a second. Definitely off. Hold that down so we can see if we can probe the outside of this connection. Right, have we got some loose wires on this plug? Yeah, if you wiggle, can you see on the multimeter, yeah, occasionally we get a higher voltage. Let's turn this off and let's have a little inspection of this. I mean, they look solid enough. That looks suspicious there in how much it's been clamped down. Difficult with testing mains power is you don't want to be fiddling about with it whilst it's live. I am tempted to chop the cable there. Let me just zoom in so you can see. This is quite a common fault that we get in the repair cafe as well, where people say that something's not working properly. It's just the fact that the cable's been crimped too much. Right, where's the where is it? Yeah, you can see there. It's not bad, but equally, it does look like it's been over tightened. So let's go back to the desk. Plan of attack. So I am going to get some of my other clips and just see what the continuity is like on this cable. Maybe this is the fault all along. If the cable has been flexing and causing fluctuations in current too much, maybe that's upset the power board. Who knows? Right, sit that one on there. Switch that across to continuity. Nothing. Straight away, that's working fine. Absolutely working fine. Let's go across the other side. So what I'm doing, I'm just wiggling the cable whilst checking. Yep, absolutely fine. What on earth? So let's go back. Make sure that's turned off. Let's plug it in. Select these two probes again. Just put them on the mat so I'm not touching. Switch that to AC. Let's switch on. Absolutely fine. Now if I wiggle, that's fine. That's all fine. Switch off. Take that off. Connect it back to the board again. Nice and secure. Switch it back on. Nothing. Let's check. We are getting... Okay, we are definitely getting 240 volts there, or a bit more, to be honest. Turn the board over carefully, remembering it's live. Right, we're getting the voltage into the board. Suspicious. Okay, the light's not lighting up. Not good. Right, let's switch across to volts DC and just see what's going into the chip. So we wanted pins 10 and 13. So pin 10 is there. 11, 12, 13. Nothing is getting to this chip. Chip pin 14, nothing. Non-volts DC, so nothing is coming across at all now. Now, did I do something wrong when I was messing about with all of these things? So what I need to do is check all my soldering, check all my work. Let's just turn it off before I get a shock. Well, actually, before I turn it off, let's just check to see what's going into that small trickle transformer. Yes, it is going into the trickle transformer, so the problem is somewhere on this side. Let's see. No. 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 So I don't know which windings are the output windings on that transformer. It's difficult to see. So there's 3 windings together by the look of it. That one and that one. Nope. That one and that one. Nope. That one and that one. Nope. Okay. Right, I'll stop recording for a bit, do a bit of probing and come back. Not quite sure where I got to with this repair in the series of the sort of videos that I've been recording. I think this may be my 4th recording. It's getting a little bit disheartened with the repair, so I think I'll just talk through where I got to. I think in the last segment, I just replaced the chip and I'm still getting some problems on the board. Not quite sure what was wrong. So I resorted to Google, resorted to using Gemini, an AI from Google, asking lots of questions. I was using Gemini a little bit before as well and getting guidance, and it's relatively good, but also it can take you down a bit of a rabbit hole when it comes to the repairs. So I'm going to switch to the close-up cam and then just talk you through the sort of back and forth that I had with Gemini. And then hopefully I might do a little bit more on the board tonight. It's been a long day at work, lots of back and forth. Had a visitor from supplier company come up to Manchester, so spending the day with him and visiting some other suppliers and things like that. So it's been quite a hectic day. Came home, had to feed the kids, tidy up, etc., etc. So yeah, I'm definitely ebbing on my energy levels. But something's turned up in the post today, so I'm quite keen to have a go at progressing this fix. And never know, could it be a fix today in this segment of the video? Let's see. So let me just switch across to the close-up cam. Now, ultimately, I think in the back and forth with Gemini was absolutely convinced that this board worked in a slightly different way, and I was having arguments with it. And I think I realised that I was using the like the fast responses rather than the pro responses. So I switched things up, started using Pro because I'm a Pro subscriber, and it then started to apologise for taking me on a bit of a bum steer. Started to get somewhere with the conversation. Then it started taking me back down the same rabbit hole it was taking me down before. So, you know, you can't beat an argument with a computer, can you? All got a little bit odd, but I think we might be getting somewhere. Ultimately, I think what we were finding was the chip was exhibiting signs that there was a short circuit on the startup sort of circuit that is effectively the components that sit around the chip. This transformer, it was convinced, oh, I've just noticed there's a component that's not been soldered back down. It was convinced that the resistors up here were in line with the startup current, etc., etc. And then it said that it wasn't, and then it was telling me that these transformers were not bridging the isolation gap. And if I turn it over, you can see there's an absolute clear isolation gap. that goes all the way down here. And that is deliberate. The reason why we have isolation gaps in electronics is we have a hot side which connects to the mains electricity, and then you have a cold side. And I think it's called galvanic isolation, but effectively means physical separation between the two parts of the board, and it prevents you from getting shock from mains voltage. Yes, the transformers bridge the gap, but really the transformers are coils of wire wrapped around each other, but they are isolated wire, and transformers effectively use sort of a magnetic power to step down the voltage, or step up a voltage, but step down the voltage from one to the other. So even though the contacts on either side of the transformer itself are bridging the gap, the transformer internally, the wires are isolated from each other, and they are passing the energy via a magnetic field rather than direct currents. The only components that do bridge the gap are these, I think they're safety capacitors. I'm not 100% sure what type of capacitors they are. Very, very low capacitance that's on there. So having an argument with Gemini, it was convinced that there should be a trace from over here to over there, and it's trying to convince me to put a jumper wire across the two, and it was all getting a bit needless. Eventually, switching up to Pro had a bit more of a sensible discussion. Lots of the discussion centered around the IC that's on here, and it was convinced that because of the pin 13 and ground was showing that there was a small path through there. I think it was 5 kilo ohms. So, relatively high resistance, but not high. So it indicated a bit of a ground to short. Lots of back and forth. And then eventually Gemini realized that the 2 pins here on the chip, oh, hang on, let me move that down a little bit. These 2 pins, so I think one of these is pin 13, so 9, 10, 11, 12, oh, hang on, 9, 10, 11, 12, 13. It was convinced that there was an issue with this to the ground pins over on this side, and we've seen them at 5 kilo ohm resistance reading. It was convinced there was a ground to short. So did some more testing. I was getting frustrated, and eventually what I did was I lifted one leg of all of the components that are around this side just to prove, and also took off all of the capacitors just to prove whether or not there was a short on the board. So eventually all of those lifted, took the IC off, checked between the two traces on the board, and there was the ground short had gone altogether. So was it one of these components? So I worked through them one by one, tested them all, made sure they were the right resistance readings or the right capacitance, and checked the ESR readings on all of the capacitors again, checked the diodes. Everything was absolutely sound. The only component that was faulty was one of these transistors, and they control this transformer and tell it how fast to switch on and off, which effectively drives the current. Carried on the conversation, and then Gemini realised that the chip it advised me to replace before, it gave me an incorrect part number for the chip. So we've had more debates about that, and we've got a new chip. So I'm hoping if I get the new chip soldered on, also get this component put back down, which I tested. And again, the reason why we lift components when we're testing is it just completely eliminates any other piece on the board. So it means that you are testing the component itself. You are not testing anything that the component might be connected to. So going to get the chip out, whack it in. I'll reconnect. There's a small, I don't know if you call it a daughter board, but there's a small board that connects with wires to this main board, and this then connects off to a temperature probe that's inside the fridge. So I guess this ultimately controls the on-off of whether this supplies power through or not. So I'm going to get all that soldered back up. I'll probably stay quiet and have a play around with some of the editing software that I've recently installed and just see if I can just fast forward through all of these elements. So if I switch maybe across to this camera, you can see the sped up process of what's going on. So I've just offered the chip up to the holes, and I can see that the legs are slightly splayed out on the chip. This often they come from the manufacturers like this. So I'm just going to find something hard to press it down against, so that I can just basically shorten that gap a little bit. You want to be careful. Try to get it done in a way that is equal on both sides, because otherwise it just becomes a bit of a pain. I've got this little mini anvil. It's not very heavy. It's not very big, but it is good for sort of bending small pieces of metal. I think it's used for jewelry normally. The beadsmith, yeah. So it's for making small pieces of jewelry, but it's ideal for sort of bending small bits of electronics. So push that down on that side and then push down on the other. See if we can get these legs straightened up a little bit. Again, make sure the orientation is correct. So you'll have a little notch on the chip itself. Maybe if I hold up to the camera a little bit and focus. Ooh. No, I'm not good enough. Okay. You'll just have to trust me. There's a little notch in the end of the chip. And if you look at the board, printed on the board itself, there's a small notch on there as well. If you ever do one of these sorts of repairs, you'll see quite clearly how it's marked out on the board and how you can recognize that the chip is in the correct orientation. Okay, so that's gone in quite nicely. I will push this leg down. Okay, so some of my favourite tools. I'm not quite sure where these came from, but effectively I think they're forceps. They you can close them, they grip because they've got these sort of ratcheted grips at the top, but they're really good. They're slightly stronger than tweezers, but not as severe as pliers. So they're really good to just grip onto something, especially electrical components. So I think maybe that there's a blob of solder on the back. So I'll need to push that through. Quite common to get burns from doing this because you hold the component with one finger, you turn it over, you heat up the solder so that you can push it through, and you end up burning your finger. So try and be careful if you are doing things like this. Those soldering gurus of you out there will be pleased to know that I've replaced the tip with my new tip on here, so you don't have to shudder every time you see me going to solder something. Genuinely don't know why I didn't do it sooner. Just laziness, I guess. There we go, that's pushed in nicely. You'll see that the board's lovely and clean on this side now, but just getting, it's bits of old flux on my hands. It was driving me mad, so I gave it a really, really good scrub in some isopropyl alcohol, or IPA, as we commonly call it. Right, okay, let me get my flux and my solder, and maybe we can just fast forward through these bits, because it's probably not that exciting to watch. Okay, right, that's everything soldered back on. Just put the close-up cam away over there. Lift those up so you can see my eyes. Actually, I think I'll take them off altogether because they look a bit odd. When you get to my age, you'll need them as well, so I'm not really going to apologise too much about wearing my weird specs. Question is, will this work without, well, will it work, but will it work without the temperature probe connected? So I'm just going to have a look down here in the fridge itself and see if, I know it's not a temperature probe, it looks like more of a variable resistor of some sort. Just trying to see if I can bring this up a little bit closer because I'm not 100% convinced. So where's all those? Let's go. So I'm just looking back on the fridge itself. Oh, crikey. Right, let's give it a go without the variable resistor on there. See what happens. What can possibly go wrong? Where's the power cable? Here we go. This doesn't work. I'll be on the brink of calling it a day for this. I think I've probably spent 3-4 hours trying to sort it, and as I've said many times, variable power supplies are my absolute nemesis. But I want to, not variable power supplies. See, I told you I'm tired. Power supplies are my nemesis. I do want to be able to learn more about them, so having the opportunity to fix one may seem strange to other people that I want to try and attempt fixing things that drive me mad, but it means that I get the opportunity to learn, and hopefully I'll be able to be a bit quicker with these things in the future. So I'm guessing this won't turn on. Yes, nothing's happened whatsoever. Oh joy. Let's have a look with the multimeter to see what's going on. Let's just switch across cameras so you can see what I'm doing with the multimeter. Get that placed down there so you can see it nice and clearly. Sometimes it auto turns off, so I've got to switch it back to volts DC. So I want to check ground. It's 9, 10, 11, 12, 13. Nothing's going into the chip. Joy. 9, 10, 12, 13. Is there anything on pin? Nope. Right. Let's just check to see anything's getting through to the power cable, because it didn't before. If you remember, I had some funnies with the power cable not putting the voltage through. Yeah, 240 volts or 246.9, so that's definitely going through there. So if I flip the board over very carefully, because I don't want to get a shock, if I then switch to test the capacitors over this side, see if they're actually charging up. 167, it says minus, but that's just because I got these probes the wrong way around. So let's just do it again so I can show you positive reading, 167. If I flip across the other side, 169. So let's see what's going on with the transformer. So I'm just trying to remember which bit goes where. So we've got a small transformer over there. Right, where it was ground. I'm just going to turn the power off for a second and just identify where ground is on the okay, so that one is ground. You can see it's Well, that's interesting. It gave a reading and it's now gone open circuit. What is going on? So that's ground in the middle. Just have a look. Oh, hang on a second. Are these capacitors the right way round? I've never removed those. Yep. Looking at the boards underneath, I can see that they are. So one pin there is right. Okay. Ah, let's measure these again. Right. Okay. So they are acting in series to make one big capacitor of 336 volts, which if you touch that, you get quite a nasty surprise. So my black probe is on this path. So this is all ground. So I can hold that on there. Let's see what measurements we're getting on the transformer. Nothing on that one. 324 on there. Check on that. So we're definitely getting voltage on this side of that small transformer. Does this give us, yeah, lots and lots of voltage. So on this side, we want to just see what's happening if the transformer's outputting anything at all. Just trying to remember where ground is. I think this is ground because that's a jumper that goes across ground, I think. So let's see what we got. 0.18 volts. 0.18 volts. So there's some voltage coming across. So does that mean that something is not telling this transformer to kick in properly? Okay, so I'm still on ground there. Let's have a look to see what's going on. That goes up to here, 0.2. Okay, not quite sure what I'm measuring. Where was the other? So we've got two transistors next to each other. Right. That's one. That's one. So there's one transistor here. There's one transistor there. Let's check this capacitor. 0.24 volts. Let's come down and check some of these other capacitors down here. Just trying to remember where they are. So just in front of that jumper is, I think, is this one of them? Getting an awful lot on that, so maybe it's this. Very little. There's capacity there. Nothing at all. And then I think that's the third capacitor. Hardly anything. So we're getting moderately more voltage than before, but we're still not getting enough voltage to get this circuit to start up. So it's either the wrong IC still, or it is something is taking the power down to ground and just soaking up all that voltage. What have we got on here? So hold this on ground for the chip. That's on pin 13. Hardly anything's getting through to the chip at all anyway. Right. Let's just turn the power off. Let's check these transistors and make sure that they are not shorted again. So chip that into diode mode. See, I think this is one of the transistors. Nothing in that direction. Measurement in that direction. Measurement in that direction. Nothing in the other. So that's good. Nothing. Nothing. Swap probes. Measurement. Measurement. Right. What is going wrong? Let's just check on here. I think this is effectively diodes as well. Nothing on that. Oh, hang on a second. Am I getting nothing in both directions on this big diode? Could that just be the board? Nothing in that direction. Am I? No, I'm not. That's why I'm not measuring the right component. It's here. Nothing. Ooh, hello. Dangerously close, those big capacitors. Nothing. 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 Do I take it off and see? Let's do that. Let's see if that is happy or not. Actually, I think that's more related to the hot voltage anyway. Let's just check. So if I remember correctly, it was getting me to check between ground and pin 13. So 9, 10, 11, 12, 13. And we are getting path. My woolly word. 9, 10, 11, 12, 13. Right, hang on. 9, 10, 11, 12, 13. Which way round am I looking? The reading won't stand still. Actually, it's now gone still. Okay, I'm not sure. I'm going to stop recording now. Probably have another argument with AI. Talk to Gemini a bit more. See where we go. Okay, speak soon. Right, so we're there. I've managed to fix it. I'm sorry that I've not recorded the fixing process. I need to talk a little bit quietly because everyone's gone to bed. It's coming up to midnight. Kids are in bed. They've got school tomorrow. They're just back at school this week after Easter holidays. So I need to do my best not to give them any excuse to say that they don't want to go in because they're tired, etc., and all that sort of thing. My wife's just gone to bed as well, so I need to be quiet. But I'm really chuffed that I've got there. Sorry that I've not filmed the last little bit of the fix. Now I will go through what I've done and how we got there. So if I just switch to my desktop browser, I can maybe talk a little bit about the conversation with Gemini that's helped me get there. But ultimately, there's been a bit of back and forth about the startup circuit. So Gemini kept asking me to check this and check that, but some of the things it's asking me to check just weren't physically on the board. It uploaded photographs. It hadn't realised that the topology of the board was one that had a different type of topology, and it was trying to tell me there should be a jumper wire from one place to the other. It was telling me that the standby circuit should have a separate IC, etc., etc. I kept telling it, no, 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 are you sure? Are you sure? So we finally got to the point where um, ultimately Gemini went, it's using a classic. Let me just switch the screen so I can show you. Here we go. Across to the browser, but instead of a modern smart chip to pulse the transformer, the board uses a dumb analog circuit called a ringing choke converter. Now, if I knew better, I probably would have been able to recognise that straight away. Power supplies are definitely not my forte, but I'm pleased I've stuck with it. So it identified the fact that the startup feed effectively comes from the primary side, from the high voltage side. It was talking about the two transistors which are in Q1 and Q2 on the board, and they are the sort of primary high voltage side. No, they are the two transistors that blew when I first did this, and that's where we got the sort of spark occur on the board. So let me just switch back to the camera so I can talk to you properly. So that's where we got the spark on the board. Actually, no, if I switch to the desk view, and I can point, you'll notice there's a bit of a mess on my desk. So excuse all the bits and bobs. Where's my little pointer? So if we go all the way back to the start, I did the stupid thing with the fuse, cause these two transistors here, Q1 and Q2, to blow. I tested those right at the outset, and I could see that they blew because I knew something was not quite right. Now, these two transistors, they operate this, what do they call it? A ringing choke converter. An analog circuit called a ringing choke converter relies on a single standalone high voltage transistor to do all the heavy lifting. Where did it come? Where did it come? It talked about the type of current that goes through. Where is it in there? Just scroll down text. So it talks about the standby circuit theory was a complete wild goose chase, confirming there was no 8-pin IC. You've handed us the final definitive blueprint of this board. So eventually it has understood everything here. So it says it uses an old school trick called a self-oscillating half bridge. So effectively, it says the kickstart topology is actually using these two transistors that does a power trickle, and it says it does a twitching power trickle and the twitching of this current, the twitch. When you plug the board in, R2 and R3, so that's these two resistors here. Force a little bit of current into Q1 and Q2, that's those two. This makes them unstable and they begin to naturally oscillate or brackets twitch on their own in completely uncontrolled by a microchip. So it's oscillation that's uncontrolled rather than a microchip actually causing them to switch. So that the twitching pushes a sloppy, this is Gemini's words, not mine, a sloppy, raw AC current through the big transformer. And then the secondary side of the big transformer generates a small voltage from that twitching. That voltage travels through a diode, fills up your C7 capacitor, which I think was this one. And that arrives at the actual chip itself. And then once it gets into that chip, the chip wakes up and then it takes charge, and then it starts controlling the whole circuit. So that's how this works. I tested the resistors across here, and I found that this resistor had actually blown. So it should be 2 ohms, but it measures at something like, I don't know, 1.5 mega ohms. So, you know, totally blown. In hindsight, I could have maybe fixed this in 10 minutes by replacing these, and then just thinking, well, what else may have blown in the vicinity of these 2 circuits, because these are definitely the 2 that weren't very happy. As soon as I tested that resistor there, found that it had failed, and rather than measuring 2 ohms, it was in the mega ohms. So I replaced the one, still didn't work. I was a bit disheartened, and then I realised that I replaced the 2 ohm resistor with a 2.2 ohm resistor, which is negligible really, but you need to have these in balance. So I changed the other resistor that was perfectly fine, brought that to a 2.2 ohm resistor, and that meant this was in balance. It started providing, what was it, sloppy AC. I love that phrase. That goes through, everything woke up. A little test bulb. So got my test bulb here. Let me move that out of the way, and then I can show you guys, so you believe me. I'm sure you believe me anyway. Proof for the pudding, etc. So if you imagine this is our fridge. Oh, hang on. Where are we? Imagine this bulb is our fridge. Turn it on. There we go. We have a load. It goes off because of you need to adjust it with the variable resistor here, which controls how cold you have the fridge. So power supply works. I just need to put it back into the fridge and run it for a little bit and just make sure it gets cold. Let me just show you my desk at the moment. Absolute mess. I've got work tomorrow, so I want to make sure this is all tidied up so I can just get up early and get work done. There's some bits that I need to get done before some meetings tomorrow, so need to make sure I can actually work as soon as I get up. And well, got to have a coffee first, obviously, but all working now. Happy days. I'm really chuffed. I'll get it put back in the fridge, and then I can give James his fridge back, and you know, he's working on both 12 volts and also 240 volts. So yeah, brilliant fix. So that's it. Mammoth video finished, and I can go to bed very soon. So yeah, I'm really happy.